When we were first figuring out how to use the fundamental theorem of calculus to calculate integrals, we noticed that basically every derivative formula gave us an integral formula as well, just by sort of running it backwards. But one derivative formula that we haven't yet turned into an integral formula is the product rule for derivatives. So let's see if we can turn the product rule for derivatives into a product rule for integrals. A quick side note, we won't call it the product rule, but that's essentially what it is. So here's the product rule for derivatives. How could we turn this into something about integrals? Well, one obvious thing to try is, why don't we just integrate both sides with respect to x? So on the left, we'll do an integral of the derivative of f times g. Incidentally, f and g here are both really functions of x. Right? They aren't variables, they're functions of x. I'm not writing the parentheses of x like this because it just makes everything cluttered. So just keep in mind that f and g are both functions of x, as are their derivatives. Okay, so integral of derivative with respect to x of f times g dx. So there's the left-hand side. On the right-hand side, we get the integral of df dx times g plus f times dg dx, and this is all integrated dx. On the right hand side, we can split up this sum. So this is integral of df dx times g dx plus the integral of f times dg dx. On the left-hand side, well, we have a derivative and we're doing an antiderivative, so these just undo each other. So on the left-hand side, we just get f times g. Now you might wonder, hey, this was an indefinite integral, don't we need to write plus c here on the left-hand side? Well, we don't, because remember, as long as there is an indefinite integral somewhere in your equation, you can sort of shuffle the constant of integration over to that indefinite integral and sort of absorb it into that indefinite integral. So we don't need to write a constant of integration here. Okay, so this equation is true, but why should this count as a product rule for integrals? Well, the integral with the product in it is over here. We sort of have a choice of which one we want to solve for, and the traditional choice is, I guess, to solve for this second one. So we'll just move this first integral, integral of df dx times g dx, to the left-hand side. And what we get is f times g minus the integral of df dx times g dx is equal to the integral of f dg dx times dx. Okay, and so what we have here is an equation where one side is an integral with a product in it, and the other side is some formula that tells you what that integral is. Well, sort of. Really, I mean, this equation that we came up with, it doesn't really tell us what the integral on the right is. What it does is it transforms the integral on the right into a different integral on the left, together with this other piece, f times g. So using this formula will never save you from having to evaluate some integral, but hopefully, if you use this equation appropriately, hopefully the new integral that you get after transforming will be easier to do than the integral before you did this transformation. So that's how we'll use this equation. We'll use it to try to turn hard integrals into easier integrals, and then we'll do the easier integral. I said that this equation doesn't get called the product rule for integrals. Instead, it gets called integration by parts. Not quite sure why. I guess because there are two parts and you are, I don't know. The name has never really made sense to me. Let's look at a couple examples of how we can use this. So let's see. So for our first one, we're going to find the integral with respect to theta of theta times cosine of theta. So remember the formula was the integral of f times, I'll write it a little differently, but the integral of f times g prime. In this example, our variable is theta, so let me write d theta equals f times g minus the integral of f prime times g d theta. Okay, so the first thing that we need to do is decide, right, we have two things multiplied here, theta and cosine theta. We have to decide which one is going to count as f and which one is going to count as g prime. And it's really up to us, right? This is written with the theta first, but we could have written the theta second because multiplication is commutative, so we could have written this product in the other order. So we have to decide which counts as which. And what this integration by parts formula gives you will be different depending on which one you put where. So what we will have to think of before we choose which is which of these pieces, theta or cosine theta, which would we rather differentiate, because f is going to get differentiated, and which piece would we rather integrate, because the g prime part, we're going to integrate it to get g for this formula. So let's see. If we integrate theta, we get something like theta squared, and that's more complicated than it started out. If we differentiate theta, then it's going to turn into 1, and that's simpler than what we started out with. So it seems like theta we would prefer to differentiate. That means cosine, I guess, would be g prime, and so we're going to integrate cosine, but integrating cosine doesn't make it any more complicated. So that seems like the right way to go. We would rather differentiate theta rather than integrate it, because it makes it simpler. So let's say that f is theta. That means f prime is 1. G prime is cosine theta. And that means g, now we have to integrate here to get g. If we know g prime, g is the integral of g prime. So that's going to be sine of theta. Now this is an indefinite integral, so you might think, hey, don't we need plus a constant here? But remember, when we use this formula, we're still going to have an indefinite integral when we're done, and so we can sort of absorb the constant of integration into that indefinite integral, so we don't need to write this yet. We will write it eventually, but not yet. Okay, now that we have all of these pieces, we can use our integration by parts formula. So it says f times g, so theta times sine theta, minus the integral of f prime times g d theta. So f prime is 1, g is sine theta, d theta. Okay, now you can see we didn't completely solve this integral, but we turned a difficult looking integral into a different integral that's easier. This integral is so simple that we know what it is immediately. So theta times sine of theta minus, and the antiderivative of sine is negative cosine theta. Now we need to write plus a constant, because now there aren't any more indefinite integrals in our expression here. And then, of course, when we simplify this, we get theta times sine theta plus cosine theta plus a constant. So integration by parts let us turn this tricky integral into an easier integral, which we then could evaluate ourselves using other tricks that we know. So as a check, let's calculate the derivative with respect to theta of what our answer was. So theta sine theta plus cosine theta plus a constant. Of course, when we differentiate, the derivative of the constant is 0, so that part goes away. To get the derivative of this first piece, we're going to need to use the product rule. So derivative of theta is 1 times sine of theta with no derivative plus theta with no derivative times sine with the derivative, so that's cosine theta. And then plus the derivative of cosine, so that's minus sine theta. And then the sine thetas cancel, and we get theta cosine theta, which was the integrand we started with. So our antiderivative, our indefinite integral, checks out. This is the correct indefinite integral. So integration by parts did work. Let's look at one more example. Let's find the integral from 1 to 2 of x e to the x dx. So we haven't talked about integration by parts with bounds before, so for a definite integral. But remember, a definite integral is the same thing as an indefinite integral. But then when you're done, you evaluate at your bounds and subtract. So we can use integration by parts on the indefinite integral and then plug in our bounds afterwards. So let's think about integration by parts for x e to the x. Remember, we need to decide which piece should we count as f and which should count as g prime. F is the one we differentiate, and g prime is the one we integrate. And so whatever we choose for f, it should get simpler when we differentiate. So which of these pieces gets simpler when we differentiate? Well, e to the x doesn't change when we differentiate it, but x gets simpler when we differentiate it. So let's let x be f. And that means e to the x is g prime. And just to check, right, g prime, that's the one you integrate. So does e to the x get more complicated when you integrate? No, e to the x, the integral of e to the x is e to the x. So this seems like a good way to choose f and g. So f is x, f prime is 1, g prime is e to the x, and g is e to the x. So, comparing this example and the last one, if you have a polynomial in your integrand and you're thinking about doing integration by parts, usually the polynomial part will be f, because polynomials get simpler when you differentiate them. Okay, so now we can use integration by parts. Remember, after we do integration by parts, we still need to evaluate at our bounds. So integration by parts says f times g, so x e to the x, minus the integral from, indefinite integral of f prime g, so that's 1 times e to the x dx. Okay. Now if you look at what it would mean to evaluate out our bounds, really another way to write this is x e to the x, right? We're going to need to plug in our bounds into that and subtract, minus, but if we do this indefinite integral and then plug in our bounds, that's the same as a definite integral. So definite integral from 1 to 2 of e to the x dx. Okay, so if you have a definite integral, you can do integration by parts. Right? You don't have to write out this step here. You can do integration by parts, but just each piece in integration by parts gets those bounds. Okay, so now this first piece we're ready to evaluate. So plug in the 2e squared, minus, and then plug in the 1 times e to the first power, so that's just e, minus, and now we need to do this, this remaining definite integral. But this definite integral is easier than the one we started with, right? That's a sign that we chose f and g wisely, because this integral we can actually do. So antiderivative of e to the x is e to the x, and we need to evaluate at 1 and 2. So 2e squared minus e minus, now be careful, we need parentheses here. Plug in our 2e squared minus e to the first, that's e. And then we can simplify this stuff. So it looks like these e's are going to cancel, and 2e squared minus e squared, that's e squared. So integration by parts is a trick that we can use to transform one integral into a different integral, and hopefully that new integral is easier to do. Although if you choose poorly, you might end up with an integral that's harder to do. Also, integration by parts, we can use it for definite integrals and indefinite integrals.